This video is going to be about the concept of intermolecular forces. If we look at that word, intermolecular, so inter means between and molecular means molecules. So these are forces that occur between molecules, like two different molecules, and how they can be attracted to each other. First, let's review a little bit positive and negative charges. You should probably recall this from physics, actually. But if we have two positively charged things, they will repel. And if we have two negatively charged things, those will repel. It's like the two same ends of magnets, right? If you try to bring them together, they'll just sort of want to bounce off of each other, they'll repel from each other. But positive charges and negative charges attract. So that's like the two opposite ends of magnets, right? If you have them like this, these two ends are going to attract and want to stick together. So molecules, in particular polar molecules, can act kind of like little magnets and stick together because they have positive and negative charges in them. So in general, intermolecular forces occur when the negative part of one molecule is attracted to the positive part of another molecule. So a lot of times we're going to be talking about if we had just like a beaker full of a molecule, you'd never really have like one molecule of water in a beaker, right? You'd have like lots of molecules of water in a beaker, tons of them, and those molecules would be able to interact with each other. You can also have situations where you have like two different molecules together in a beaker or a cell or whatever, and those molecules can interact with each other. So these intermolecular forces are not bonds, so it's not a permanent, fusing of those molecules together to make a new molecule. It's not a chemical reaction. It's an attraction, a temporary attraction between those two molecules or parts of those two molecules. So these are forces that make them kind of stick together, but they are, that was a wavy line, they are weaker than bonds, not as strong as real bonds. So with real bonds, we might represent those with a straight line. With an intermolecular force, instead of a line, we might represent that with a dotted line to show that it's like not actually a bond, it's not as strong, but there is still something there. So like this dotted line would represent an attraction between these two molecules, but not a bond. So there are three types of intermolecular forces with varying strengths. So we're going to start with the weakest one, which is called dispersion. Sometimes it's called London forces or London dispersion forces. So you might see those different ways of writing it. But let's start out with an example, really simple atom, helium. If you look at the periodic table, you should see that helium has 2 electrons. And now we know electrons repel because negatives repel negatives, so generally we would expect helium's 2 electrons to kind of be hanging out on opposite sides of the helium like this. However, electrons are constantly moving, they're constantly buzzing around in their little orbitals, and sometimes, maybe just for a second, just by chance, we might end up with both electrons on the same side of the helium, like this, just for a second. So if that happens, think about what does that mean for the charges on the two sides of the helium? Well, what that means is the side of the helium with the electrons is going to be a little bit negative over there, and the side of the helium without the electrons is going to be a little bit positive over there. So we have this temporary, very brief polarity that happened just sort of by chance for an instant. And now if there's another helium nearby, and there probably is because we don't have usually just a single atom of helium, then maybe it just happened to be doing the same thing at the same time. And if it was, those two heliums could be attracted to each other. The negative side of one would be attracted to the positive side of another, and we would get this temporary little attraction between the heliums. And so we would call this temporary little attraction dispersion force. It's a weak intermolecular force. Heliums don't generally stick together very well, but they do, a tiny bit. So other nonpolar molecules can do this. They can stick together a little bit due to this dispersion force. The next type of intermolecular force, and the next strongest, is the dipole-dipole force. And this is when you have a polar molecule, like here's a polar molecule HCl. So it should have a negative side and a positive side. The chlorine is more electronegative than the hydrogen, therefore the chlorine pulls the electrons more strongly, therefore the chlorine is a little bit negative. Hydrogen has less electrons, so hydrogen's a little bit positive. When you have molecules like that, and again we have like a whole beaker full of HCl's, not just a single HCl most likely, these HCl's will be attracted to each other. The negative chlorine of one molecule will be attracted to the positive hydrogen of another molecule. And then we do this dotted line to represent that there is an attraction there. Not a bond, not a full-on bond, but they kind of stick together. And so if you have a lot of HCl's all in a beaker, they're all kind of sticking together, negative end to positive end, and those molecules tend to stay, kind of stuck together in a clump. And they're still sort of moving around and breaking these dipole bonds and forming new dipole bonds. They're kind of doing that in the glass, but at any given time, a lot of them are sort of sticking to each other. So this is the second strongest intermolecular force. It's stronger than the dispersion force. And this will happen with any polar molecule. The last and strongest type of intermolecular force is called hydrogen bonding. Now it's a little bit of a misnomer because it is called bonding, even though it is not a true bond, but it is a pretty strong intermolecular force. Hydrogen bonding is really just a strong dipole-dipole. It's a dipole-dipole where you have like really polar molecules, where there's a big difference in electronegativities between one atom and the other atom, and so you get a molecule that's like extra polar, and so those will stick together more because it's kind of like stronger magnets. This occurs when we have hydrogen, which is really not electronegative, bonded, so connected to an oxygen, a fluorine, or a nitrogen, which are the most electronegative. So if we have molecules that have that pattern, they can form hydrogen bonds. And the classic example of that is water, H2O. So we've got really not electronegative hydrogens and really electronegative oxygens. So oxygen has a pretty strong partial negative charge, and hydrogen has a pretty strong partial positive charge. And when we have, a glass full of water molecules, the negative oxygen of one molecule is attracted to the positive hydrogen of another molecule. And they form these hydrogen bonds, and they tend to stick together. And so since water is very polar, water sticks together very well. You might notice that if you put a drop of water on a surface, it will bead up like this, because all the water molecules are kind of clumping together. If you put a drop of something like rubbing alcohol on a surface, it will just kind of flow out and spread out because the rubbing alcohol molecules are not as good at sticking together because of the hydrogen bonding as the water molecules are. So this property, hydrogen bonding, gives water a lot of its properties that make it useful for life. The fact that water just likes to stick together. Hydrogen bonding is also used in DNA. So DNA has like two sides, and then the bases are joined in the middle. So right here, where like an A joins up with a T, those are connected together by a hydrogen bond. If you have a G and a C, those are connected together by a hydrogen bond. So all your DNA down the middle is all connected via hydrogen bonds. All right, so now let's practice identifying which intermolecular force would you expect if you had, a beaker full of each one of these molecules. So you can pause the video and take a second and try to answer it yourself. But now I'm going to go through. So if I'm trying to figure out, which intermolecular force is affecting this, the first thing I want to think about is it polar or is it not polar? So HF is polar. We definitely have two different sides to that molecule. Cl2, that's non-polar because both sides are the same. And pH3, that is polar because this side is different than that side. It's actually shaped like a pyramid sort of thing because those electrons up there are going to push the bonds down. It's going to push the hydrogens down. Okay, so if it is nonpolar, the only force that could affect it is dispersion. So Cl2 is not going to have very strong intermolecular forces. If it is polar, then I need to look at, well, can this form a hydrogen bond or not? Does it have N, O, or F attached to hydrogen? This one does not. This one does. So this one is going to be forming hydrogen bonds with other HF molecules. This one is polar, but it doesn't have hydrogen bonded to N, O, or F. So that means this one will do the dipole-dipole force. So why do intermolecular forces matter? The intermolecular forces present in a molecule really affect the properties of that molecule a lot. They affect how easy it is to boil or evaporate some of that molecule. They affect how thick or thin that molecule is as a liquid. And they also affect how easy it is to melt that molecule. So you can try to guess what the effects are on each of them. You can pause if you want, but I'm going to go through them now. So generally, remember, the stronger the intermolecular forces, the more those molecules are sticking to each other. So if the molecules are sticking to each other really well, it's going to be a lot harder to boil or evaporate them, because when a molecule evaporates, it means they're going from all together in this beaker or glass or whatever and flying off separately into the air as a gas. So if they're sticking together more, it's harder to boil or evaporate them. And we say that means they have a higher boiling point, so it boils at a higher temperature. This is one of the reasons that water, again, is so important for us. Water is pretty hard to evaporate relative to some other molecules, like, say, the rubbing alcohol, for example. Rubbing alcohol evaporates really quickly compared to water, and that allows water to exist as a liquid, and we need water to exist as a liquid. If the oceans were just boiling away really quickly and easily, that would be a problem for us because we need that liquid water. Generally, things with stronger intermolecular forces will be thicker. We would say they have more viscosity, so kind of more like thickness or syrupiness. It would be harder to run your hand through it. Again, because those molecules are sticking together more. And then generally, things with more intermolecular forces or stronger intermolecular forces are harder to melt because, again, they want to stay together as much as possible, so they will have a higher temperature that they melt at. All right, so that's going to be the end of intermolecular forces. You'll have a practice activity after that.